Good morning or good afternoon, my dear students. Now it's one step toward the termination of this module. It's now lecture number 6 out of 7 lectures in this module. The title of this lecture is Bipolar Junction Transistors. Let's start. Okay, if you remember in the previous lecture, we were talking about the MOSFET or the metal oxide semiconductor field effect transistor. We consume actually 2 lectures in order to understand the energy band diagrams, the different region of operation, the metal oxide the semiconductor energy band diagram interface, the threshold voltage, the pinch off, and all this stuff till we reach to the IV curve of the MOSFET. Now we are going to repeat somehow the same procedure while we are talking about the BJT or the bipolar junction transistor. Honestly speaking, in the bipolar junction transistor, we will not go into details or into the same depths like we did for MOSFET. However, depths will be a little bit lower due to now the difference between the importance, actually, let me say, between the BJT and the MOSFET. The MOSFET, as we said, it's a main building unit in any digital or many of the analog electronic circuits. Now the BJT somehow takes some steps to the backward. Now BJT, historically speaking, BJT was the first invented transistor by Shockley in 1946, where he received the Nobel Prize in 1951, I believe. But currently the importance of the BJT got somehow down. Its application is now limited to power electronics application and some analog application. That's why in many courses like what we did here, we start to study the MOSFETs first and then we proceed to the BJT. Historically, the BJT was the first and then MOSFET comes as a second chapter. But now MOSFET are more important than BJT. By the way, in the next chapter, which is our terminating chapter, chapter number 7, we will deal with a new type of transistors called the T-FET or the tunneling field effect transistors. Okay, let's now go into the details and let's now go to the bipolar junction transistors, or what is famously abbreviated by BJT. Let's now start with the schematic. As you can see here, we have now an N substrate, and then we have a P doped region and another N doped well. So if you make a cross-sectional area from, or a cross-sectional cut from this point, you will find an NPN junction, which is one of the 2 types well known for the BJT. Here we have an NPN junction. In this NPN junction, we have the emitter terminal, the collector terminal, and the base terminal. Something like we did in the MOSFET. However, we have to remember that basically MOSFET is a 4-terminal device. It includes the source, the drain, the gate, and the body. Most of the time, the body is either connected to the ground or connected to the gate. But here, the BJT is basically a 3-terminal device, as you can see, and this is a famous circuit model for BJT. I believe you deal with such a model either in electronics 1 or the electronics 2 courses in your previous years. Actually, we have another type for the bipolar junction transistor, which is a PNP junction. Here we start with a B substrate, and then we have an N well, and finally we have another P well. That's why we have a PNP MOSFET, or BJT, and here you have again the emitter, the collector, and the base. And this is the circuit model. As you know, in the case of the NBN, we have the current directed, the arrow directing with a current going into the emitter. However, in the BNB, the current is outgoing from the emitter, as you see this arrow. So this is the basic schematic, or the 3D and the 2D schematic for the BJT. Now, what about the functionality? What about how these MOSFET, how this transistor is operating? In which condition these transistors should operate. So in order to understand this, we have to return to what we usually did, which is the energy band diagram. Now let's turn with the NBN. Actually, in this lecture, we will take the NBN as a reference. However, you can repeat what we will do here on the BNB transistor using the same procedure as well. So this is a NBN transistor, as you can see. Now I start to plot the energy band diagram. As you remember, I believe you remember, we have first to make it under thermodynamic equilibrium, and the sign for thermodynamic equilibrium is we have a constant flat Fermi level. Now, as you can see, in the right-hand side, in the left-hand side, the Fermi level is more close to the conduction band, which is a sign for an n-doped material, while with the in-between region, we have the Fermi level more close to the valency band, which is a sign for the p-doped region. So this is a thermodynamic equilibrium energy band diagram. No electrical field, no electrical potential, no electrical field is applied. The Fermi level is flat. Now we are start to think how electron will move. Or we should first ask the question, at this state, do we have a carrier transport? Let's start to discuss. Here we have a plenty of electrons, and here we have a plenty of electrons, but these electrons are not able to pass to the collector side due to this building potential in the BN junction. And here the same, this electron will not be able to pass this barrier due to the building potential. Again, the same is applied for the holes. These holes is bounded here because, as you remember, the energy of the holes is increasing by going downward. So these holes is bounded, as it see here, some potential on the left hand side and some potential in the right hand side. So at steady state, no electrons will be able to move either from collector or from the base or from the emitter. No majority carrier will move, and we will have a depletion region. We have also to remember a very important note. This note actually we will use it till the end of this lecture. The NBN BJT is simply two PN junction. If you make a clear cut here, if you divide this junction by two, you will find a NB junction and a BN junction. So it's simply two diodes. Here we have an emitter base junction, and we will have a base collector junction. So starting from now till the end of the lecture, we will deal with our BJT as two connected diodes, two connected NBBN junctions. So let's now start describing what should we do. Now we have to concentrate what is our target. Our target is to push this majority of electrons to move from the emitter side to the collector side. If the electron will move, then we will have a current. This is actually our target. So our target now is to make this electron move. How can we make this electron move? Then we will make this by two conditions. The first is that we will connect a battery, like that. Now we are dealing with the second junction, which is the base emitter junction. As you can see here, I'm connecting a positive terminal to the collector, which is N side, and I'm connecting a negative terminal to the base, which is B side. So in this case, I am forcing the collector base junction to be a reverse bias. When the collector base junction is a reverse bias, then the amount of this potential will increase. The depletion region will increase. So you will find here a higher potential, and also you will find a higher potential, and also you will find a higher depletion width in the base collector junction. So this is the first step while we are dealing with the base collector junction as a reverse junction. Okay, so now please remember again, the base collector junction is a reverse junction. That's why you have a huge potential here. But let me ask a question now. Now we have a carrier transportation. We have a carrier that can transport The answer simply is no, because this electron is still bounded due to this potential, and this electron, of course, now it's highly bounded because this electron will see this huge barrier, this huge built-in potential. So electrons will not move, even holes will not move because holes is still bounded either from the left or from the right. The holes are bounded. So neither electron nor holes will be able to move. That's why we need another step. So the first step was to bias this base collector junction to be a reverse bias. Now, what is the second step? Simply, the second step is to get rid from this potential. How should I get rid from this potential? I will get rid from this potential if I make this junction, which is a emitter-base junction, if I make it a forward bias junction, then I will get rid from this potential, which is the second condition. So as I mentioned, we need two conditions in order to make current move. So now this is the second condition. I connect the positive terminal of the battery with the base, which is p-type, and I connect the negative terminal of the battery with the emitter, which is n-type. So now the emitter base junction is forward, and now you have electron which moving first from the emitter to the base, and then from the base to the collector. Then you have an overall flowing of electrons from the emitter to the collector through the base. And the condition you need is first you set the base collector junction as a reverse, and you set the emitter base junction as a forward, and then you have a current moving. This is the most famous condition for a BJT, and we call that as an active mode, or typically the forward active mode. So the forward active mode is a mode when the base emitter junction is in forward bias and the base collector junction is in reverse bias, and you have electrons passing from the emitter to the collector through the base. And then, based on your information, when electrons pass from the emitter to the collector, then the current is flowing from the collector to the emitter, which is the reverse direction of the motion of the electron. So this is simply what we have, or this is simply the process of motion of the electrons. But here you have to remember that you also have holes. And as far as you put this junction in the forward bias, then holes will also be able to move from the base terminal to the emitter terminal, because now the potential has been tackled by this forward bias. So holes will be able to move. That's why we call this transistor as a bipolar junction transistor. The word bipolar comes from here, because in the bipolar junction transistor, the current is the contribution of the motion of the electrons and also the motion of the holes. That's why it's a bipolar, it's a double polar. Both electrons and holes contribute in the current. You have a current flowing from the collector to the emitter, and you also have a current flowing from the base to the emitter. That's why it's a bipolar junction transistor. Please remember the MOSFET. In the MOSFET, it's a single pole current. In the N-channel MOSFET, the current is only due to electrons. And in the B-channel MOSFET, the current is only due to holes. While here, the current is due to electrons and holes. However, we can easily say that the current due to electron may be more important than the current due to holes. But it is still, there is a current due to holes. Now, let's say the back side or the negative side of this junction. Someone may ask me, oh yeah, please take care. Now you have an electrons. This electron will move from the emitter to the collector to the base. But please don't forget that the base is a p-type material. So in the base you have a plenty of holes. You have a majority of holes in the base. And you have now electron passing, a majority of electrons. So there is a big probability of recombination here. Some electrons may be attracted to the hole and recombine. And this recombination is some sort of losses, Because, for example, if you have 10 electrons passing from the emitter to the collector through the base, when 5 recombines, that means that only 5 electrons will reach the collector. So you lose some of your current. What should you do in order to get rid from, or to eliminate, or to reduce this recombination? In order to reduce this recombination effect, actually double action should be made. The first is to make the emitter highly doped with respect to the base. What I mean, to make this N plus in a plus region. What I mean by N plus is to make here the number of electrons is in the emitter is much greater than the number of holes in the base. So, for example, trivial example, if you have 1 million electron in the emitter and you have, let's say, 10,000 electron in the base, if all the 10,000 electron recombine with the 10,000 hole, nothing will be changed. So you will have 0.999 million electron here. So it's something like 0.01% reduction in current, which can be ignored. So by making this junction highly doped with respect to this junction, you eliminate the effect of the recombination. Another effect or another actions that you can take in order to eliminate the effect of recombination is to decrease the thickness of the base. So when this thickness is very short, electron can pass this area, which is the base area, with a lower probability of recombination. So again, by increasing the doping of the emitter and by controlling or by narrowing the thickness of the base, you can control the recombination effect, which is a drawback effect for an NBN junction. Now we understand what's called the active mode of operation. Let's now turn to the IV curve of the BJT or the bipolar junction transistor. Before going to the IV curve, usually in IV curve, we have different regions of operation. If you remember in the MOSFET, for example, you have the triode region, you have the saturation region, and you have the cutoff region. So we should expect something like that in BJT. However, what we only study in this lecture up till now is one mode, which is the active forward mode. But we also have another mode. Frankly speaking, these other modes are not so important like the first mode, which is the active mode. But let's now remember what are the conditions for an active mode. The condition for active mode is to make the first junction, which is the emitter base junction, to make it in the forward bias. And to make the second junction, which is the base collector junction, you should make it as a reverse bias. So if you apply these two conditions, you will have an energy bandogram like that, and then you will have a forward active mode or active forward mode. Then, what about other conditions? You can simply say that this is two diodes. So we have basically four alternatives: forward reverse, reverse forward, forward forward, reverse reverse. So we should have four regions of operation for the diode. This is true. We have four regions of operation of the diode. However, again, the active forward mode is the most interesting mode in BJTs. Let's now try to somehow pass quickly on the other three modes of operation. Now let's do this very simple exercise in order to understand the IV curve of a BJT, I'm sorry. As you can see here, this is the IV curve. We have a collector current here. We have what's called the VCE, or the voltage between the collector and the emitter, here in the x-axis. So this is the x-axis, this is the y-axis. Again, flashback the MOSFET. Here was the AD drain current, and here was the VDS, the voltage between the drain and source. So typically the same. Here we have the collector current, and here we have what's called the voltage between collector and the emitter. In flashback, in that MOSFET, we have different, or a family of curves at different VGS. Here we have a family of curves at different VPE. typically the same. So here we have VPE and here we have VCE. Now, in order to make this experiment in the lab, you enter your lab, you put a MOSFET on a breadboard, you start to put two different variable DC supplies. The first one is connected between the base and the emitter, and the second one is connected between the base, the collector and the emitter. This is the two DC supply. Okay, so let's turn back. In order to work in the active mode, we have to put the base emitter junction in a forward bias, which means that the voltage potential here should be greater than the built-in potential of the junction. This is a definition for a forward bias. So, for example, let's say let's say that this built-in potential is 0.7 voltage, for example. So, if we insert here 0.7 voltage, then we guarantee that we have our base emitter junction is a forward. We have now satisfied the first condition. The base emitter junction is forward. Now, what about the second junction? Let's, for example, put this voltage, which is the VCE, let's put it 5 volts. Okay, so this is 0, this is 0.7 forward, this is 0, this is 5. So what about the base emitter junction? What about what about the base collector junction? What about this junction? So let's examine it now. Here the voltage is 0.7 and here the voltage is 5. So higher voltage is connected to the collector with respect to the base. One side voltage, one back side. So higher voltage is connected to the collector with respect to the base. That means that this is a reverse biased junction, because now you have a 5 volt here, you have an 0.7 volt here, so the positive voltage is supplied or is connected to the collector. The collector is an N-type, that's why this junction now is reversed. So as far as you put 5 voltage here, that means that you have a reverse junction as a collector base junction, and that means that your MOSFET or your BJT is working in the forward active mode, as you can see here. Okay, let me now start to decrease the voltage applied to the collector emitter junction. Okay, let's now make it like that. So let's put now 3 voltage. So this is 0, this is 0.7, and this is 3. Still the voltage on the collector is greater than the voltage on the base. So still this junction is working as a reverse. This junction is still working as a reverse, then this transistor is still working as an active forward transistor. Okay, let's now decrease this voltage to be 1 voltage, for example. Okay, so this is 0, this is 0.7, and this is 1. Again, the voltage on the collector is still greater than the voltage on the base, and this junction is working as an active mode. But what if you decrease this voltage to be, for example, 0.2 volt? You put 0.2 voltage on the voltage between the collector and the emitter. So this is 0, this is fixed to 0.7, but now this is 0.2. So higher voltage now is connected to the base with respect to the collector. So now this battery is somehow reversed. You are connecting this in the positive, and this is the negative. So that means that the base collector junction is now in the forward bias. If the base collector junction in the forward bias, that means that somehow this energy level of the N-type goes upward. Then we will talk, or we will see, or we will say that this is what's called the saturation mode. So the definition of the saturation mode, which you can see here, when VCE is very small, this saturation mode is related when the emitter base junction is forward and the collector base junction is also forward. In this case, we call it a saturation mode. Another mode, which is the active mode, we studied in details, occurs when we have a forward bias in the emitter base junction and a reverse bias in the collector base junction. Now we tackle 2 out of 4. What about the remaining 2? So what if the voltage applied here is still smaller than 0.7. So this junction is not forward. So no electrons will pass. So we'll have no current. And this is basically what's called the cutoff mode. So when the base emitter voltage is smaller than the built-in potential, which is usually 0.7 for silicon transistors, then you don't have current anymore, regardless if this reverse or not, and then you call this an cutoff mode, which is easily can be seen by plotting a right line here, that when VBE is smaller than the built-in potential, you don't have current anymore, which is a cutoff region. The fourth region, or the fourth type of operation, actually is not widely known, not widely important, actually, which called the reverse active mode, where you have a reverse voltage on the emitter base junction, but a forward voltage in the collector base junction. Actually, this is totally out of our interest in this course. So mainly we are talking about the active mode. We understand the meaning of the saturation mode where both junctions are forward, and we also understand the meaning of the cutoff mode when both junctions are reverse. This is the IV curve for a bipolar junction transistor. Now let's turn to the second part of this lecture, which is what's called the Eber-Mole bipolar junction transistor model. It's a very famous model in order to model the behavior of the transistors. Most probably PSpice or CAD, Mentor tools, and all these stuff, all these simulation tools use the Eber-Mole model or the EP model in order to model or simulate the performance of the MOSFET transistors, or sorry, of the BJT transistor. Okay, let's now start to understand this EM model. As I previously said a few minutes ago, maybe, in this lecture, we are dealing with the bipolar junction transistor as two diodes. So, what EM model demonstrates is typically the same. First step, they start to model our transistor as a two die. As you can see here, we have a base. This base is the center point. Then you have, this is a p-type. This is actually a model for an NBN transistor or BJT. So this is the base, and then you connect this base with a terminal here, which is emitter, and so this is the direction of the forward from the P to N. And again, this is the base, and this is the collector, so this is the direction of forward from B to N. So this is simply the model. As you can see here, this is the VPE, or the voltage between the base and the emitter, and this is the VPC, which is the voltage between the base and the collector. Typically, the same we demonstrate one slide ago, if you remember, when we were calculating the voltage drop here and the voltage drop here. So this is the start. This is the EM model. Then, what we did is we are now trying to understand this BN junction. But please take care. There's a very big difference between studying an isolated PN junction and a connected PN junction. So if these BN junctions are isolated, then we will make it like that. We will say that, okay, we have a base, we have a base, and we have a emitter, and the direction of the current is from the base to the emitter. We have a base, and we have a collector, and the direction of the current, if it's assumed to be forward, is from the base to the collector. This is the forward direction here, this is the forward direction there. This is the equation, typically the standard equation you use for diodes, if you remember it from 2 lectures ago, or maybe you remember it from year 1. So this is two totally isolated diodes, but the case is not like that. These two diodes are not isolated diodes. They are connected diodes. And these connections make a very important role in the motion of the current. That's why the Ebers and the Mole model reach this diagram. as you can see. So let's now start to understand this diagram. Let's first start to reflect what we understand or what we understood in this energy band diagram with respect to these arrows in this p-n junction or in these two dots. First, we say that we have electrons. These electrons are moving from the emitter to the collector through the base. So you have this arrow, as you can see. This arrow indicates the motion of the electron from the motion of the electron from the emitter to the collector through the base. This is very, very, very easy to understand. So this is the first arrow. And as you can see, the direction of the current here is the reverse of the direction of the electron. So electron is moving from the left to the right, so current is moving from the right to the left. This is the first model. Then, as we can see also, we say that we have holes, and this hole can move from the base to the emitter, because this junction is forward if the model is in active mode. So you can see this direction. Electrons can move from, holes can move from here to there by this direction, as you can see. So this is the motion of holes from the base to the collector. And then this is actually what we know. This is what we understood. But please remember that you also have holes here. This is an n-type, that's true, but still you have holes where holes here is a minority carrier. So as the energy of holes is going like that, so holes here will move from the emitter to the collector. Holes here will move from the emitter to the collector. So you have holes flowing from the emitter to the collector, as you can see. So these holes flowing from the emitter to the collector. And also, you have electrons here. You have electrons here. So these electrons will move from the emitter to, sorry, these electrons will move from the base to the emitter. These electrons will move from the base to the emitter. So what about this and what about this? Again, let's describe it again. We have here we have a minority carriers. So we have electrons passing from the emitter to the collector. We have a hole passing from the emitter to the collector, this direction. And also we have holes, we have in the p-type electrons, this electron will move from the base to the collector. This is the motion of electrons from the base to the collector. So here we have the motion of the minority carrier. And as you can see, this motion of minority carrier is indicated in this model. Okay, so how can we reflect? This is the equations. Of course, we will not focus a lot about the mathematical equations as we did usually. You are not required to memorize these equations. This is simply a huge equation which represents a diode equation, and this is the saturation current. But let's go forward to this model. This is a very simple model representing a diode. But in addition to the diode, you have another current, which is a reverse current, representing the reverse process of the minority carrier. So if this junction is in the forward, then you will have this something like a short circuit, and then this current has no meaning. But if this is a reverse, this is an open circuit, and this is the dominating current. So, for example, when the transistor is working in the forward active mode. Let's now return back. The forward active mode is the mode where this junction is forward and this junction is reverse. So we have the emitter base junction is forward, we have the base collector junction is reverse. So what will happen? So this junction is forward. So this is simply a short circuit. We don't need this current source, but this is a reverse, so we need it. So as you please try the pointer now. This is the collector. Electron will move like that. Or sorry, not electron, current will move like that. So electron will move in the reverse direction. So current will move here. This is a reverse current, and then move here. This is a forward current. And actually, this is typically what we did. This is a reverse current. This is a forward current. So in the act, for example, if I told you please plot the EP model in the active forward mode, then it is simply this one. You don't have a diode here, and then this one is a short circuit, and you don't have this current source. What about the EP model in the reverse, in the saturation mode? In the saturation mode, then you have a current from here, then this current will be split. Something will go this, and another will go that, because here both are forward. What about the cutoff region? In the cutoff mode, this is working and also this is working. So you have current from here, you have current from there, and this is the base. No current will pass because now you have three currents into one node. It's not correct problem. That's why you have no current. So you can express various types of operation of the MOSFET, or sorry, of the BJT, I'm sorry again, when you're using this EP model or EM model in order to understand the operation of the MOSFET. Now, this is the second part. Now let's turn to plot the minority carriers using this model. I don't know if you remember the minority carrier plotting we did in the PN junction lecture, but it's good now to revise it. Now let's start with the active mode. In the active mode, if you remember, we say that we have one junction forward and another is reverse. Now what I'm going to do is to plot the minority carriers only, the graph representing the minority carrier. So in the emitter and in the collector, I am interested with the holes because holes are the minority carriers. So if you remember from the BN junction, we say when a junction is a forward bias, then we have huge number of electrons coming from the N side, huge number of holes, I'm sorry, coming from the P side to the N side. That's why the minority carrier increase, if you remember. That's why you have this curve like that. If you remember, we name this region as delta B, which is the excess minority carrier, and this PN node is the steady state or thermodynamic equilibrium value. So this increase represents that this junction is forward. And as you can see also here, this increase represents that this junction is forward because holes travel, and a huge number of holes travel from the P side to the N side, so holes increase, and a huge number of electrons travel from the N side to the P side, so number of electrons increase. Now, what about this junction? In this junction, we have a reverse bias. What do we mean by the reverse bias? That more electron will leave this P, more electron as a minority will leave this P and will go to the N because this is a reverse direction. And more holes here will leave the N and go to the P. So as you can see, number of minority carriers decrease here, a number of minority carriers decrease there, and this is a sign that we have what we can call a forward active mode. So for example, I can either give you this plot and told you please state what is this mode, or I can ask you please plot the minority carrier concentration for a bipolar junction transistor when it's in the active mode. Again, please try to think why we are interested in the minority carriers only. Please try to think this. It's a very important question. Why here I'm interested to plot only the minority carrier? What about the majority? I will answer it, but at the end of the lecture. Now, so let's now return here. This is the active region, forward, reverse. So forward, reverse junction, as you can see. So this junction is forward, this junction is reverse. So this is an active mode. So let's go to the next one. Here, as you can see, okay, now we have, okay, this is a reverse junction because the number of holes decrease. And also this is a reverse junction because the number of holes decrease. So in the right hand side and the reverse left hand side, both are reversed. Then this is a cutoff. This is a cutoff region because, or the cutoff mode, because both holes in both sides are increased. That's why it's a cutoff region. So let's now turn to the third. Now these holes increase, these electrons increase, then we have a forward bias here. And now these holes increase, these electrons increase, now we have another forward bias. So it's forward bias here, it's forward bias there, then it's double forward bias, then it's a saturation region. Another important question. Why we have this like that? Why it's not straight line like that? Please think about it. Also another important question. But let me answer the first question now. Why we are interested in the minority carrier? We are simply interested to the minority carrier because changes affects only minority carrier. If you remember from the p-n junction lecture, we said that when when electrons move from the majority to the minority, the majority of electrons will not be affected, but the minority will be affected. So usually in semiconductor devices, minority carriers are the indication for any effect or for any impact because they can easily be changed. However, majority are very huge number, so will not be affected. So usually we are plot the minority carrier, not the majority carrier. Okay, then it's the end of this lecture. Thank you very much for your concentration. Now we terminate the BJT lecture. I hope you enjoy this lecture as I enjoy it. Now it's we have only one chapter remaining, as I mentioned before. It's the tunneling field effect transistors, the TFETs. We will make it, I believe we can make it in one lecture. So hopefully next week, maybe we finalize the course in this semester. And I wish you great luck, and please enjoy this lecture, and see you in the next lecture.